Hey, what's up everyone? This is going to be the first video in a series where we build a self-driving car. So the goal is to use machine learning and deep learning to design an algorithm that can play this racing game and play it well enough to put up some good times and maybe even be comparable to a human player. I'm not sure how well we'll do and how possible it is, but it's going to be a fun project. So I got the inspiration or the idea from another YouTube channel called Centex. It's this guy who's been doing this for a while, and he's a great resource for Python programming tutorials. So if you're into Python and you haven't checked out his channel, you definitely should. It's pretty comprehensive, goes over all sorts of areas of Python, from machine learning to Django, GUI programming, plotting, everything. So the series I'm referring to is the Python Plays GTA 5, where he makes a deep learning network to play Grand Theft Auto, to drive a scooter or a car around around the city. And yeah, so I'm going to be using a lot of code that he's already done and try and recreate and possibly improve on his algorithm. So the game that I'm using is called Assetto Corsa. It's a racing game. I got it on Steam for 15 bucks. I got a racing game instead of GTA 5. One reason, it was cheaper, 15 bucks. And the other reason is I was thinking of possibly using an evolution model where we use metrics such as lap time, car damage, things like that to evolve the network so it learns to play better, where you have like this scoring or like a health meter. The better it does, the healthier it is, and then you propagate those models. But I don't know if it'll work. But yeah, so I chose that game. You can choose any game you want. And so yeah, let's get started. If you go to this guy's name's Harrison. If you go to his Python Plays GTA 5 series, there's a link to his GitHub, so we can get some of the code that he uses from there. So what we're gonna need is grab screen and direct keys. Grab screen is a function that lets us take screenshots of the actual game window, so then we can do our processing for our algorithm. So go ahead and click on it, copy paste, save it into a new Python file. One note is that this thing is for this is only for Windows. It's using some Windows libraries, so if you're on Mac or Linux, you're going to need to find a different way to do it. But yeah, so grab that one, grab direct keys. This is for our key pushes, so it's for the controls left, right, forward, things like that. It allows Python to press keys. So just copy paste, move that into another file. So I've already done that, and so I have grab screen, direct keys, and then I created a main function. So a lot of this is already discussed in Harrison's video, so I'm going to try and go through this relatively quick and just highlight the changes that I made. So first let me comment some of this out. So let's see, the imports you'll need is OpenCV, import the direct keys, get the press keys in the release key function. From grab screen, import grab screen, grab underscore screen. Then we need NumPy, PyAuto GUI, and then we're going to use sklearn's cluster so that we can use that k-means method. I'll show you what that's for in a sec. We're also going to use threading and time. So yeah, if you don't have them, pip install to get them. Anaconda has most of them, so it's a good choice to start with. But anyway, so I started with a function called main and use the if name equals main if statement at the bottom. So in the main function, I created a while loop, infinite loop, and then so the first line is just a timer. So at the start of the frame, create a timestamp, and then we use it to measure the frames per second. Then the next line is we're going to use grab screen to capture an image of the game window. So what you'll need to do is pass a tuple or a list with the coordinates of your screen, the top left, bottom right. So I did that. I saved it as a tuple that has 2 coordinates. One note is using a 4K screen, so sorry if it's a little small, but I tried doing this in 1080p, and even though my screen resolution set to 1080p, it was still rendering a large number of pixels. So it was, instead of 800 by 600, it was 1600 by 1200. So yeah, I set it back to 4K. Sorry if it's too small, but anyways, that's how you grab your screen. And then first thing we're going to do is just show the image. So we're going to create a OpenCV window just to show screen. And yeah, let me comment these out. And then there's also a print statement to print the frames per second. So we're just taking the difference of time.time minus our time marker and doing 1 over it to get frames per second. And then the if statement that allows us to press Q and close the window. And yeah, so if I go ahead and run that, I should just have a window that it matches exactly what this one does. You can see we're getting, I don't know, 50 frames per second. Sorry if that's too fast to read. So the latency is pretty good, not laggy or anything, which is what we want. So that's good there. The next thing to do is to do the processing. So that's done by another function called process image. We pass in screen, and then we'll display the process screen in another window. So I'll go up here to processed image function, and the first processing we're going to do is the canny edge detection with OpenCV. So we take the original image and we use canny edge detection to do the edge detection. What this returns is a black image with just the outlines of everything highlighted. These parameters, threshold 1, threshold 2, will affect how many lines you get. So let me just go ahead and show you what that looks like. So here's our original image, and then here's our edge detected image. So you can play with threshold 1, threshold 2 to get rid of some of this grainy stuff. It's picking up the details of the road, which we probably don't want, but you can see it does a pretty good job of just getting that outline of everything. So that's edge detection, pretty straightforward. And yeah, so next bit of processing that we're going to do is cropping the image, because when we're driving, we don't really need the sky. Anything above the horizon is not needed for the algorithm. You don't look up too much when you drive. You're looking at the road and what's in front of you, and a bit above the horizon is not really needed. So we're going to crop our frame to get rid of that. And it also saves us a lot of CPU, because the bigger the frame to process, the more CPU you need to use. So it's just more efficient to process a smaller image. So we use an ROI function to just crop the top out. It's explained in Harrison's video, so you just need to I created a NumPy array with the vertices of the area that we want to crop. So I just refer you to refer to his video for it. So Let's just see what that looks like. So yeah, you can see I cropped out the horizon and I cropped out the hood of the car. Actually, so the view I use is where is it? Yeah, I was using this view. So I cropped the hood and I cropped the horizon. So yeah, you can play with the views. It's gonna, if you're using a different game, it could be totally different. So you'll need to figure out how to crop your frame. So the next thing is the line detection. So we've done edge detection. Now we're going to take those edges and approximate them as lines, just straight lines. So the first step in doing that is to pre-process it with a Gaussian blur. So it just kind of blurs the image to make the lines, I don't know, it evens out the differences, and so it doesn't get, these small noisy bits don't trick the algorithm into thinking there's a line there. So we do the Gaussian blur. I might try and move the Gaussian blur ahead of here one time, but for now I'm kind of following what the other series did. So we blur it, and then we use this thing called off lines P, O lines P, something like that. So we take our blurred image, and what this does is it looks at all those edges, and it puts a line where it thinks there's a line. So you'll get a list of, I don't know, sometimes it'll be 20, 30, 40 lines in the image. So, and then there's these other parameters that you need to pass it. So just refer to the OpenCV manual on what these are for. I'm not sure what this thing looks like, some conversion to radians or something. Not sure what that is. For some reason you need this empty list. And then this is the minimum line length and minimum line gap. So you can play with these to get more or less lines, make it more sensitive, less sensitive. So yeah, and that'll give you a list of lists of lines. It's kind of weird. OpenCV, like, instead of a list of lines, you get a list, and then inside that is another list, and then inside that is all your lines. And that kind of, like, for the k-means that we're going to do next, that kind of is a problem. So what I did was I used a line comprehension to just unpack it a little bit, and so now instead of lines I created n lines, and it's a list of lines instead of an extra layer of lists. So it just kind of unpacks it. So yeah. So yeah, now I will display the lines that the O lines thing does. So go ahead and run that. Wait. Hold on. End lines. Oh yeah, sorry. So yeah, once you get the lines, I have a draw lines function. So we have to draw them onto the image. So draw lines is right here. There's some other stuff here, don't worry about. So for now it's just going to draw the lines on top of the edge detected image. So yeah, you can see we've got a bunch of lines popping up here. Let me just kind of drive around a little bit. So yeah, you can see the lines kind of show up, and there's, I don't know, a few of them. But a good thing is we're still getting like 20 frames per second ish, which is good. The gameplay and like, if I look in this window, it's not too bad. It's not laggy, which is what we want. So yeah, so far so good. So the next thing, this is where I deviated a bit from Harrison's video. So when he did his like first go at control, he had like this really long function that would take all those lines and try and group them and approximate them and bring it down to just 2 lines. So a line for the left lane and a line for the right side of the lane. But I was just looking at the code, and it was very nested if statements, nested for loops, and it looked kind of complicated, and I don't know. It didn't seem like it was the way to go. It was maybe just to get something real quick and dirty. So I tried to do something a little different. I used the k-means algorithm from sci-kit learn. So what k-means does, well, the reason why I did it was because if you look at the lines, they all kind of look like they're pointing towards the horizon, towards the vanishing point. So we should be able to just approximate them as two lines, and it should be pretty close to what Harrison got. So that was my idea, and I tried it out. So just to give you a quick overview of k-means, let's say you have a bunch of points, like just a list of points, and I've drawn them sort of suggestively. So if we have a bunch of points and we say we want to group this into two groups, we can use k-means to do that. And the way it works is you take your list and then you say how many groups there are. In this case, I'm saying there's two, and then you just take two random starting points. So I say starting point here, and then you go through each point and you say which starting point is it closer to? Is this point here closer to this one, or is it closer to that one? And then well, let's use this one for example. This red dot is closer to this yellow starting point, so we say it's a part of that group. And you do that for all of them, and then once you do that, for your new two groups, you take the centroid, and then what that does is once you take the centroid, you shift your starting points to the centroid, and so now you can see it's a much better approximation for the groups. And so you do this over and over again until your centroid converges, and then you basically have a nice point in the approximate center of your groups. And that's what we're going to do with these lines. We're going to say there's two groups of lines, we're going to use k-means, and we're going to sort of approximate them as two groups. So yeah, let me show you the code first. It's really simple. We call k-means from our sci-kit cluster group. So where was I? So we say k-means, we say that there's two clusters. We say random state 0, I forget what that's for, and then we fit it with the end lines. So this was the main reason why I did this statement here, is because I needed it for the k-means algorithm. But yeah, so we're fitting that group of lines into two groups, and that's it. It's just a one-liner, and then we draw. Now we're gonna draw the k-means results. So this k-means dot cluster centers, this is just two lines. So it's taken all those 20-30 lines and compressed it down, or approximated it down to two lines. And now we draw those. So let me go ahead and show you what that looks like. Oops, what did I do wrong? I did draw lines here. So yeah, get rid of that draw lines and just keep that draw lines. So yeah, let me make the lines a little bigger, the way Harrison had it. So okay, so you can see we have just two lines, and it's approximately right and left side of the lane. And let me just kind of those lines sort of, yeah, I mean they seem to be pretty well stuck on the lanes. This game, the track is, sometimes it gets wide and sometimes there's extra lines, so it gets a little fooled by it, but more times than not it works. So the last step is to actually the drive control. And this is where I deviated from his design also. So what I do is, once I do the draw lines, I'm also calculating the slopes of the lines. So I have a function to calculate the slopes. It's just take the line, do rise over run, and get the slope, and return it. And then I put those two slopes in a list. So yeah, so then what I do is it takes that list of slopes and I call it drive function. So what drive does is it takes the sign of them. So it just if the slope is like -3 and I take np dot sign, I just get -1. If it's +3, I get +1. So you just get either a +1 or a -1. And so it's just returning the sign. And then I take the sum of those. So I'm either going to get a +2, a -2, or a 0. So if it's -2, that means both slopes are negative. That means I need to go to the right. If I get a +2, that means they're both slopes are positive. I need to go left. If it's 0, that means I'm in the center of the lane and I need to just go straight. So these right, left, straight are all functions. So if I go to them, so for example, straight, when I call this, what it does is it creates a thread. So the reason why I did threads is because when we do the control, you need to add a pause. You need to press the key, hold the key for a short amount of time, and release. So if your program's running in just one thread, that pause is significant enough to where it's going to drop your frames per second to, it was dropping me to like maybe 5 or 6 frames per second. And before we were up at 20. So this was my method for getting around that and keeping the frames per second high, is to do the driving controls in separate threads so that the main thread can keep running at full speed and just doing these little tweaks, little driving things on the side in a separate thread. So I call straight, I create a new thread with a target function t keys for thread keys, and then I pass it the arguments that it needs. So for straight, the first argument is the one that you press and hold, and the other two are the other two arguments are what the keys that you release. So if I get the straight call, I go and execute target key or thread keys, T keys, and then I press the straight key. So I press that one, and then I release the other two, and then I pause for a certain amount of time. So it's a press and a hold. And it's the same thing for all of them. They all reuse the T keys function. So the first for right, the first one is the press and hold. The other two are the lift or the release keys. And yeah, and then so you just call the thread. You create the thread with the target function and arguments, and then you start it. And that's it. That's the whole algorithm. So with this function, it's basically, I'm about where Harrison was on video 5, I believe, where he had something that kind of drives. So now let me show you its performance. So let me go ahead and just run this. So we're driving, I'm not touching the keyboard. Type error, none type. Where is that? Oh, okay, I need to move this into here. Yeah, that's why I have the type error here. Okay. All right. Okay, try 2. Oh crap. Oh well, it's working. It was just stuck on right, but now we're let's call it there. So you can see, oh, and then hits those keys a few too many times. Gotta, like, when you end, sometimes it's still pressing the keys, so you gotta press them a few times to release it. So yeah, that's it. That's where I'm at right now. The next step is to generate training material and train a model or train a network. So next video we'll hopefully have something cool new to show. But yeah, hope you guys liked the video. If you have any questions, let me know in the comments. I'll try my best to help. And yeah, see you guys soon. Peace.